Okay, to sketch a normal curve, you start with your z-axis, and you write down 0, and you do a dotted line above 0. And then you equally space some points on the left. Call this one -2, -1. Call this 1, call this 2. You then plot a point right here. And then where z equals 1, you plot a point that's at 60% of the graph altitude of this one. Now where's 60%? Well, it's a little more than halfway. So if this is halfway, 60% would probably be about here. So this will do just fine. Okay? And on this side, you do the same thing because this curve is symmetric with respect to a vertical line through 0. Okay? Over here, as explained, and some of these details are on your worksheet, you want something that's between 1/8 and 1/7 as high as this. I think that's kind of hard to do, but you know that if you subdivide this and then subdivide it again in half, divide this in half, divide this in half, you've got 1/8, right? And just a little above 1/8 would be 1/7, so you've got a point here, and you do the same thing over here. Okay? Make sense? That's an easy set of instructions to follow. It's going to be a short video. The last thing I do is I draw a smooth curve, a bell-shaped curve, that starts asymptotic to the z-axis, comes up here like this and ends up asymptotic to the z-axis, meaning it's going to pretty much join up with the z-axis as far as you can see with your eyeballs over here, even though it never actually reaches the z-axis. It's going to get so close that you can't tell that it's not the same place. Okay? So this is your normal curve. Now there's more. Z equals 0 is where your mean goes. Z equals 1 is the mean plus your standard deviation.
Do you mind writing a little bit? Sorry.
That was a bad timing, but yes, go ahead.
Do you mind writing a little bit bigger? I can't. Or can you?
Yeah, I got it.
Here, you want to switch seats with me?
You're good.
I don't want to take the time to rewrite it, but I'll write this one bigger.
Okay.
Okay? This would be mean plus 2 standard deviations, right?
Yeah, yeah.
Okay? And what do you think this would be?
Mean plus 1
Negative.
standard deviation, or
Minus.
minus 1
Yeah,
standard
mean minus a standard deviation, mean minus 2. I'm not going to write that down, but that's what it means, okay? Now, you remember that yesterday, my average SIP was around 14 grams, maybe. So, if your mean is 14, the standard deviation, I think, was 2.6. Okay? What number goes here?
Oh, well, 14.
14, because this is the mean, right?
Yeah.
Okay, so, now this is the z-scale here. And that's not written very well, but these numbers are your z-scale, right?
Yeah.
Okay. I'll say X is SIP size. The mean value of X is 14, the standard deviation is 2.6. There are notations for that we'll look at, but right now I just want you to see how this picture works. Okay, so the mean is 14, so I'm going to put 14 right here. Now it really should be below the axis, but I didn't leave myself room, right?
Yeah.
So 14 goes here. Now everybody think, don't say, what number's going to go here? What's this say? What number is it going to give you? What do you think?
16.6.
16.6. Why? Because the mean is 14 and the standard deviation is 2.6. And this says mean plus 1 standard deviation, right?
Yep.
And over here is the mean plus 2 standard deviations. 2 times 2.6 is 5.2. Add that to 14, and that's going to be 19.2. And we could label them over here, right?
Yeah.
Now,
11.4.
if, listen, if this is a normally distributed variable, the SIP size, more of my SIPs will be between here and here than are between here and here, won't they?
Yeah.
How many more? What ratio? Well, it's the ratio of this area, well, this area to this area, whatever, right?
Mm-hmm.
How can you calculate these areas?
Well, one of them's 34. I
Well,
don't-
yeah, but where'd that come from? I've given you all the information you need to calculate it,
Yeah.
okay? Let me explain. N of Z is 1 over the square root of 2 pi times e to the negative z squared over 2. The e to the x button is right there in your calculator waiting to be used, and it's appropriate to use it because e's a totally irrational number,
Wait, really?
and raising it to a power is something you can't do by hand anyway, okay?
What does that say on the top?
Z squared over 2. And do let me know if I'm writing too small, as you did, okay? If you can't read it, we'll fix it. All right?
Hold on.
Now, how would you calculate, okay, the other thing is, well, I want you to do the thing. To calculate the area
Negative C?
between here and here,
Mm-hmm.
if you evaluate n of 0, you get something very close to 0.4. I ask you to verify that by doing it in your calculator, okay? So you don't have to necessarily believe me. N of 1 is approximately, this is approximate, 0.24. And N of 2 is approximately 0.05. Okay? So how could you calculate the approximate area of this region and this region?
Rate of change?
Do what?
Rate of change?
Rate of change? Good thing to think about, okay? But actually, we're doing areas.
So you just multiply it by 2?
I'm sorry?
Multiply it by 2?
Here's what you do. Here's what you learned today. How close is the area of this trapezoid to the area under the curve?
Pretty
Really
close,
close.
pretty close.
Yeah, it's a little low, but, you know, maybe just 1% low,
Yeah.
right? Now, can you do this trapezoid? Well, this is 0.4 and this is 0.24, right? And you do that area, well, 4 and 0.24 is 0.64, and half of that is 0.32, and you multiply that by 1, you get 0.32, which is close to your 0.34, isn't it?
Yeah.
Okay? So that's kind of where it comes from. Then, we can do the same thing here. In this case, it looks like the curve dips a little below this, So we would overestimate the area, okay? And we would get 0.145, okay? So the point is that by treating these as trapezoids, we can get the area. And the area and the ratio of these areas could be checked out against my SIPs to see if the right percent of SIPs are here and the right percent are here. Okay? That make sense?
Yeah.
If the SIPs are normally distributed, which a number of things are, then that's going to work. Now, if you want to get more accurate results, what can you do? You could make more trapezoids, because if you make more trapezoids, they're going to stay closer to the curve, aren't they?
Yeah.
Okay? So, you know, I could do this. I could say, okay, well, let's do another trapezoid. Let's do this one here, and this one, and now we're really close to the curve, and let's do this one, and this one. That corrects most of our error, doesn't it? Mm-hmm. And you've got this thing, you can put z equals 1/2 in there, it's going to work, right? And if you want really accurate, you can go over to Excel and do as many intervals as you want. And you can reproduce the normal curve tables you use when you study statistics, just from this function, okay? So there are a lot of connections. The main thing now is I want you to have this picture, and I want you to see how to construct this and practice drawing it. You know, just draw it 3 or 4 times using the instruction I gave you. It's a profoundly important curve, and the use of it is as important as anything else you're likely to learn in mathematics, unless you become an engineer or a physicist or a chemist or an economist or something, okay? Or a researcher. You know, if you're doing research that involves mathematical analysis, well, statistics is really important, and right there's the basis for a lot of it, okay?